we present Senscon, a physiological sensing system that incorporates electrodermal activity and photoplethysmography measurements into VR controllers. VR allows for the manipulation and control of diverse stimuli in virtual environments as realistic as possible. Besides immersing users in VR, different responses can be triggered for users, like engagement, presence, arousal, and workload. Evaluating these factors is pivotal in UX research in VR. Therefore, we often use questionnaires or implicit, real-time assessments, such as physiological measures like PPG and EDA. Those physiological measures allow quantifying to assess physiological arousal, emotional valence, or cognitive workload in VR. Current scientific measurement standards require medical-grade devices, where their signal recording quality comes at the cost of limited ecological validity and artifact sensitivity. Previous work already showed the viability of embedding physiological sensing in the VR system. For example, Bernal et al. Embedded multiple physiological sensors in the HMD. However, there is a lack of validation studies to evaluate signal reliability of embedded sensing. Finally, current work is either limited to consumer-grade devices or is not applied to VR environments. In this paper, we present Senscon, a physiological sensing system that incorporates EDA and PPG measurements into VR controllers. In contrast to bulky medical-grade equipment, Senscon allows for an easy and ready-to-use system that minimizes the user's preparation time. We first ran a study investigating how users hold VR controllers to identify ideal sensor placement for EDA and PPG. We found that 64.1% of the front, 73.1% of the back, 87.1% of the right side, and 57.1% of the left side are touched by at least one participant. We then calculated the area which all 12 participants touch for successful sensor placement. Here, we found that 47.8% touched the middle area of the right side of the controller, making it optimal with high overlap for sensor placement. After this, we integrated the PPG and EDA sensors into two HTC Vive controllers into the areas with the highest overlap. For the communication and local sensor control unit, we use an ESP8260-61 Mini 2 microcontroller offering both Wi-Fi and Bluetooth connectivity. For PPG sensing, we used a pulse sensor device for PPG raw data acquisition soldered to a ESP82. After implementation, we evaluated the Senscon in terms of usability, user experience and acceptance, in the first phase of the study. After this, we compare the measurement accuracy to medical-grade devices across 6 different VR tasks. We chose this condition as seating rest is recommended as a baseline condition in previous research, while standing triggers orthostatic stress. This task was designed to evaluate the effect of natural body movement on data quality. This task was included to test the influence of hand movements on the signal quality together with the general movement of the entire body. This task was chosen to recruit working memory resources and physiological stress responses. We used the VR Stroop task as it was confirmed to evoke cognitive stress by semantic interference. We evaluated the signal qualities of 2 sensors for measuring EDA and PPG embedded in a VR controller across tasks that are known to either be sensible to artifacts or to elicit specific autonomic responses. Moreover, we supplement with results from questionnaires on usability, SUS, acceptance, UTAUT, and Likert scales on UX. Users reported that Senscon had significantly better perceived usability as compared to medical-grade device. Regarding acceptance, Senscon was well received in terms of performance and effort expectancy. attitude toward using technology, behavioral intention, and diminished anxiety. When evaluating signal accuracy for ETA, Senscon showed no difference across tasks when comparing the difference between standardized tonic ETA between Senscon and the medical-grade device. Similarly, for the PPG signal, heartbeat detected with Senscon did not differ across tasks when comparing the differences in heart rate between the two devices. In conclusion, Senscon is a good trade-off between signal quality and usability for physiological sensing in VR. We envision different future applications for Senscon for VR adaptation, physical activity recognition and DUX assessment.